All right, hello everyone. Welcome back to Physical Geology 1403. Today is lecture 2. Before I jump into that, a couple of things. The syllabus was not working the last time we met. It should be working now. Can anyone confirm that? I went through all of the garbage that I had to yesterday to try and get that going. Basically what happened was I was really proactive and I submitted the syllabus for approval a week before classes started. But then naturally, a few days before classes started, they went in and updated the system assuming that no one had done that yet. So all of my syllabi were washed away. And then no one bothered to tell me they had done that. So class started, there was no syllabus, it's working? Great. So basically on Tuesday afternoon after we met, and then yesterday morning I went in and redid all of the syllabi for all of my classes. All of the information should be there now, everything you need for that syllabus quiz. If the syllabus quiz is a little late, don't worry about it. I will take note of the day that you did it, and I'm gonna sprinkle some fairy dust on that. It's not a big deal, okay? But yeah, I'm sorry that happened. Oftentimes there are forces outside of my control in the world of programming that make my life difficult, and all we can do is roll with the punches. Okay, we had lecture 1 last time we met. Any questions about the stuff we talked about then? We went over a brief introduction to geology in general. Anything that you want to talk about? And you know what? It doesn't have to be about geology, science at all, or anything that's happened in the world, right? I'd love it if we got comfortable enough with each other here that we could just like talk about stuff that happened in the world. It'd be really cool. There is crazy stuff every day happening in the world. That's very true. Do you have an example?
I saw a video of an anti-ICE protester get shot in the face with a non-lethal weapon.
Yes. Oh, yeah. Yeah. What happened to the protester?
He got dragged away by a city.
Mm-hmm. Did he die?
He had to get surgery in his eye.
I guess so. There was a video he got shot in the face because he was just at a protest, and it was like one of those salt. I think it was like one of those like salt guns or something.
Mm-hmm. Yeah.
And he literally like got dragged away on the ground by a city, and they were like he was like choking.
Yep.
That's like most of my 40 page.
Most of your what?
40 page.
What's that?
Oh my gosh.
You don't have TikTok?
I don't have what?
TikTok?
I do not.
Okay. It's like on TikTok, Instagram, like whatever your For You page is like.
It's the algorithm.
It's the algorithm you built off like what you like and what
That word alone is why I don't use TikTok. I don't have a TikTok. I don't have an Instagram. I don't have a Snapchat. I have a Facebook that I made when I was like 16. I check it maybe once or twice a year. I just don't. I mean, social media has some benefits. It lets you stay connected to the world, but these days, most of the world that you see isn't real. So I prefer to use the sources that I can verify for myself, because no one bothers to verify their sources on social media. But very interesting. Yeah, there are protests all over the place right now. It's everyone's right to protest. It's not everyone's right to protest violently. And whether or not there is any response from law enforcement, violent or otherwise, it's their prerogative to make that judgment, not my own. I personally took part in many protests in Washington, D.C. when I was there. They were always peaceful. They were demonstrations. They were not anywhere close to riot status. It seems these days it's difficult to start a protest that doesn't turn violent one way or another. And I'm sorry to see that we've descended that far.
There's also a lot of Donald Trump AI, and honestly, I hate that part.
Yeah.
It's so funny.
There's a lot of AI on both sides spreading misinformation. You can make pretty much anything.
It's, the Donald Trump AI that's on like my TikTok is weird videos that make him look like a girl dancing.
Right. Yeah. There's also a lot of misinformation, though. You can make. Have you seen those pictures, those videos, those advertisements on YouTube? It astonishes me that this is legal still, of actors or politicians, like making like it looks like they're doing a commercial for some kind of product. Those are all fake.
Or like deepfakes.
Yeah. There isn't a single politician or celebrity in the world in their right mind who would make an advertisement like that for a weight loss pill or something, or phallus enlargement pills. Let's say that, right? Anything like that. There is nobody that would do that and put it on a YouTube video. Those are all AI deepfakes, and it boggles my mind that is still legal. That should not be legal, but yes. Those are not there? Good to know. I will.
What is the huge link on there?
The huge link, is it at the top? I'm going to bet that's the link to my CV.
It does say that on top of it.
Okay, yeah, that's presumably the link to my CV, which someone at our AOC Global office, which are the people that look over Blackboard, they said that they were going to fix that, and I'm guessing they did not. Okay, CV link, and what did you just say? The points breakdown. Luckily, you all already know the points breakdown because I gave it to you on Tuesday.
Yeah, it says right here, it's like the item and categories, but under points and percentage, there's nothing there.
Okay, I'll go in there and fix that later. Oh man, first week, right? Everyone's favorite. All right, great, yeah. Anything else we want to talk about?
The first lecture slide, that was just an introduction to everything we're going to go over.
General overview of the class as a whole.
Okay, cool.
Yep. Now, today we are starting on specific information. Before we do, are there any other questions though? I always want to make sure we get conversations. Nothing? All right. I'll wait for our friend here to take a seat, and then we'll go ahead and get started. It was Adriel, right?
Yes.
All right. Adriel or Adriel?
Adriel.
Adriel? All right, cool. It's like Adriel. It sounds like a biblical angel name or something. You guys ever watch Supernatural? No? Oh, man. Don't say Unk. Fantastic show. Ended a few years ago. Went for 15 seasons. So cool. But it sounds like the name one of the angels in there would have had. Okay. Let's begin. Last time we talked about the big macro scale view for the most part. We looked at the science of geology as a whole. Okay. Well, we're zooming in right now. We're going to look at the smallest component of all of this. Okay. And then we're going to zoom back out from there and talk about each individual component. All right. What is the smallest? Let me rephrase this. Matter. What is matter? The correct answer is nothing. What's the matter with you? Come on, guys, keep up. Okay? No. But thank you. I have a guy. All right. Yes, good. You're going to love my class. All right. Yeah. Atoms. Exactly. Atoms are the smallest unit of matter that we are going to discuss in this class. Anything smaller than an atom goes quantum. And while I'm happy to discuss quantum things here, that's not within the bounds of this class, and we'll save that for a tangent I go off on later on. Okay? An atom, though, is a particle made up out of 3 smaller units: protons, neutrons, and electrons. Protons and neutrons collectively make a nucleus, and the electrons form an outer shell. Okay? Protons have a positive electric charge. Electrons have a negative electric charge. Can you guess what charge neutrons have? Neutral. No thing. They don't have a charge. Great. Chemistry. Good. By the way, everything in my class is going to assume that you've had at least beginner chemistry and physics. Those are supposed to be prerequisite to my class, assuming that you've had at least high school level of chemistry and physics. If you have not, you'll get just the basics that you'll need to keep up in this class, but I'm going to assume that you've had some experience with those so far because you were in a college level class, okay? Could you remind me of your name? I'm sorry.
Ulani.
Ulani, that's right. Great. Okay. Where was I? Oh, yes. Okay. So, learning about atoms. Electrons. Let's talk about electrons for a second. Electrons are the smallest of these units in our atom. They are only about 1/2000th the size of a proton. Neutrons are the largest. They're slightly bigger than a proton. Okay. But electrons zip around our nucleus made out of protons and neutrons extremely fast. I have it on here, I think. Yeah, about 1,360 miles a second. So quickly that it's practically solid. It feels as if it's a solid barrier. As a matter of fact, things have substance because the electron shells of the atoms that make this hand are interacting with the electron shells of the atoms that make that hand. And then the same with this desk and anything that you come in contact with. The electron shells give it that interaction, that barrier, okay? Now, when I say electron shell or orbit, people typically think of something like this. Don't think of it like this. It's not, each electron is not a moon that's following a particular orbit around the nucleus. That's the wrong way to think about that. That's not particularly solid either. There's lots of space there for things to go through, okay? Instead, when I say electron shell, think of something like this, where each electron is zipping around in this seemingly random direction so quickly that it makes a solid shell around the nucleus. Okay. Depending on which atom we're talking about, it's going to have, or each element I should say, it's going to have more than one electron shell. Multiple electron shells. Lots of electron shells. The only one that we really care about in this class is the outer one. Can you think of a reason why we would care about the outer electron shell more than the inner ones? This is a clue here. The ones on the surface are the ones that do what? Yeah, the ones that interact with each other. It's the outer electron shells are the ones that interact with other electron shells. The inner ones, they have function, and we care about those a lot more in physics and chemistry. But in geology, where we're talking about how these atoms bond, spoilers, we're talking about bonds next, okay? When we talk about that, we care about the outer shells, because those are the ones that will bond with each other. Okay? We call that outer electron shell the valence shell. Okay? So let's talk about our periodic table of elements here. How often do you think about elements? Periodically.
Oxygen, that's it.
Yeah, you think about them periodically. Right? That's the boo. Okay, man, that got a boo from the dad joke lover over here. Okay, great. All right, so as of right now, we have 94 natural and 24 synthesized atoms on our periodic table. What does that mean? What are synthesized atoms? Well, what? Man-made. How can we make an atom? How can we make an element? Well, we've got these really cool things that we call colliders. Okay? There are some really big ones in Europe. And in these colliders, you basically supercharge an element, spin it really quick, zip it around a racetrack that's about 100 miles long, right? Over and over and over and over and over. And then collide it. It has to hit something. It collides with a barrier, usually a thin barrier of gold or something else. And then, oh, sorry, I just hit the microphone. Sorry if I just deafened my entire online class. Okay. Once it hits that, it creates a whole bunch of new particles. And we capture the wavelengths of light given off by those particles. And that tells us if there was anything new made. And using this process, we made 24 brand new elements. Now, they have to exist for at least, I think, what is it, like a picosecond? Which is tiny. Like you have a second, and then you have a millisecond, and then you have a nanosecond, and then a picosecond, right? But if it existed for any amount of time at all like that, we made it successfully, and therefore it goes on the periodic table. We've done that 24 times. We made 24 new elements. Now, the 94 natural ones on the Earth or somewhere else in the universe, right? Okay, here we go. All of these, okay, are naturally occurring elements for the most part. Okay, now we differentiate these from each other based on a few characteristics. Atomic number. Do you know what the atomic number is? It's the number up here, okay? In the case of hydrogen, it's this 1. In the case of helium, it's this 2. What?
Like when it was like discovered, right? Like in what? In like chronological order?
Actually, no.
No.
No. Good thought, but no. It's based on the number of protons in the nucleus. So how many protons does hydrogen have in the nucleus? 1. How many protons does helium have in the nucleus? 2. And there they go. No. Huh? Yeah, there you go. Now, why are they zipping back and forth across like this? I'll talk about that in a minute. But here's an interesting question. How do we know that we have found all of the naturally occurring elements? Is it possible some are missing?
I mean, there's still so much of the world unexplored.
Can anyone think of a reason why we have no reason to believe that there are other elements? Naturally occurring ones, anyway. Our strongest evidence to believe that we may have discovered pretty much every naturally occurring element out there is the fact that this is done. Is there a space where, like, did we go from 40 on the periodic table and therefore 40 protons to 42 without having 41? No. No, we have niobium right there. Every space in here is occupied by an element that has that number of protons. There is no awkward gap anywhere. This is our strongest evidence to suggest that we have found probably all of the naturally occurring elements. Okay? Now, your atomic number, dictated by the number of protons in the nucleus. What happens if I change the number of protons in my nucleus? What do I get? If I take hafnium and I add a proton, what happens? Yeah, I get tantalum. Because that's the next one up with the next number of protons. I do I can't think of a single trick question that I typically ask in my classes, okay? No trick questions here, just straight science, all right? So, the protons determine the atomic number of my element. So, that being said, let's talk about bonds. How do elements bond with each other? What did I mention earlier? There is a particular shell that the atoms have that conducts those bonds. What was it called? The valence shell. Okay. Now, what forces are going to push my atoms to form bonds with each other? Generally speaking, the strongest force that does so are heat and pressure, which are going to be two forces we see a lot in this course because they are very common here on Earth, okay? So heat and pressure are going to cause things to make bonds. There are 3 types of bonds you're going to learn about: ionic, covalent, and metallic bonds. When an atom forms a bond with something else, it generally does so because it is seeking stability. This is a very common theme you're going to hear. In general, all things in nature are seeking a state of stability. Okay? So, jumping back to our valence shell. Valence shell being the outermost shell of our elements. Let me introduce you to the octet rule. The octet rule states that atoms tend to lose, gain, or share electrons in the valence shell until they have 8 valence electrons. Why 8?
Because that makes a full valence shell.
Why does it make a full shell?
I don't know. They really like even numbers.
Oh, here's the question. I don't know either. And neither does anyone else as far as I'm aware. Why 8? Because that's a law of the universe, apparently. Here it is.
As much as it fits.
Maybe. But here we are. 8 electrons in the outermost shell. So you're going to gain, lose, or share electrons until you have that number satisfied. And at that point, you have become stable. There it is. There's that pattern. Okay, stable. Yeah. Okay, so now let's talk about what that has to do with our periodic table arrangement. Column 1. All of these are in this column because they have one valence electron. Hydrogen has one, lithium has one, sodium has one, so on and so forth. Everything in column 2 has two valence electrons. Everything in column 3, what do you think? Oh, I just told you I don't do trick questions. That was a trick question, sorry. No, we skip over those because those tend to all be metallic, okay? And then we come over here. Column 13, which is really column 3 as far as the valence electrons care. That's why these ones are subset, okay? This has 3 valence electrons. 4, 5, 6, 7, 8. Whoa! These ones. Why do we have these ones over here? How many valence electrons do they want? They want what? And how many do they have? So how many do they want? Yeah, they're not actually looking for any more. We call these noble gases. These are inert. They do not react typically with other elements because they do not seek to form new bonds. Helium, neon, argon, krypton, xenon, radon. Matter of fact, if you have a very volatile something like an explosive, a very, very volatile explosive, and you don't want it to react with anything, you'll usually store it in an inert gas like one of these because you're not afraid that there's going to be some accidental reaction. Okay? Okay, so how many electrons does column 1 want? 7. How many electrons does column 7 want? 1. Oh, doesn't that sound like a match made in heaven?
I'm guessing that column 1 tends to give their 1 valence to column 7.
Ooh, okay, let's look at an example of this. Okay, let's talk about our first type of bond, ionic bonds. And an ion is a positively or negatively charged element, okay? Or atom, excuse me. A positively or negatively charged atom. In this example, an electron is given. So, sodium, which column? Therefore, how many valence electrons? Chlorine, which column? Therefore, how many valence electrons? How many does it want? How many more does it want? Yeah, it just wants one more. Sodium and chlorine make sodium chloride, otherwise known as? Salt. Bingo! Salt, an extremely common bond we have on our world. Something everyone and everywhere needs. Camera, don't be doing this to me again. Stay with me now. It really is, but it's thinking about it. Okay, sodium chloride, very common bond. You get a sodium, you get a chlorine. The sodium gives its gives its electron to the chlorine. So the chlorine now has 8 valence electrons, and for that price of entry, the sodium gets to hang out with the chlorine in a bond. But now it's happened. I have lost an electron, which had a negative charge. So my sodium, having lost one negative charge, is no longer neutral. It is now positively charged. My chlorine, which was neutral before, has gained an extra electron, which has a negative charge, meaning that that chlorine is now negatively charged. This positively charged sodium and this negatively charged chlorine are now bound together like magnets. Opposites attract in nature. And just like that, I saved you a lot of time and money in marriage counseling. You're welcome. Okay? Opposites attract. Okay. There we go. This is an ionic bond. Okay? Covalent bonds are when two atoms come together and simultaneously share the electrons in the outer shell. So the easiest example to explain this is hydrogen. Hydrogen has 1 electron in the outer shell. It wants 8, ideally. But when hydrogens come together, they will often make what is called hydrogen gas. When you get hydrogen gas, the 2 electrons are equally pulled towards each other's nucleus. And so you end up with 2 electrons in the outer shell that are zipping back and forth between both of these, giving you H2 hydrogen gas. That is a covalent bond. The last one is a metallic bond. In a metallic bond, all atoms of the same substance in a given mass are going to share equally their valence electrons. Those valence electrons are able to freely flow through that material. What do we call the free flow of electrons through a material? Conduction. That's fine. I'm okay if you read it off the board, as long as you get the idea. Metals are conductive. We're familiar with this concept, right? You ever gotten zapped by electricity from something? That thing was probably metal. Plug it in your toaster. Bzz. You ever see that blue zip whenever you're plugging something in or pulling it out, like a hairdryer or something? Yeah. That's electricity. Do you know what that blue zip is? That blue snap? Trillions of electrons you just witnessed jump from your wall socket to your plug. The passage of electrons is electricity. That's what we use to power pretty much everything in our world now. Okay? Metals, because of their unique ability to share their electrons equally among each other, make conductive materials. Gold being the best one. Gold is extremely conductive. Best type of conductor we've got out there. The one that's easily, well, less and less easily obtainable anyway. Then there's silver and copper. Copper, very conductive, very good, much more plentiful than gold and silver, and so we tend to use copper as the major conductor. If you ever took a look in some of the more advanced technology that's required to be extremely reliable, like an Apache attack helicopter or something, it's like a $400 million piece of equipment right there. A lot of that cost comes from the fact that every conductor in there is mostly gold, because the last thing you want is 8 Marines crashing out of the sky on a $400 million piece of equipment because the electrical system failed, right? So you make it out of the best stuff. Servers, the high-end servers will have a gold conducting in them, right? Things like that. Okay, any questions about bonds? Well, now let's move on to talk about another change that atoms can experience. What happens, remind me, we just talked about this. What happens when I change the number of electrons in my element? What does it become? It does. Losing an electron makes you positive, gaining an electron makes you negative, and that makes you an ion. Positive or negatively charged ion, right? So, gaining or losing electrons makes you an ion. What about gaining or losing a proton? That makes you another element. Exactly. But there's one other kind of particle we haven't talked about yet. What was it? Neutrons. What happens when you gain or lose neutrons? No!
That was a very enthusiastic way of telling me I'm wrong.
Should I tell you in a different way?
No, that's fine.
No.
Okay.
How about that? I'll be enthusiastic, because that's just who I am. Okay. No, what happens is you change your mass. Okay, what do I mean by mass? So we talked about atomic number, which dictates the number of protons. What about this number? That's atomic mass. The mass is the total mass of protons and neutrons. And I mean, on this periodic table, it also has the total mass of the electrons, but the electrons have 1/2000th the mass of a proton, so it's tiny, which is why this often will go out. I mean, look at this. It goes out to 5 decimals. We're not going to mess with that. Okay? Ignore the mass of the electrons for the most part. We're just going to concentrate on the mass of the protons and the neutrons together, which is your total atomic mass. Okay? So here we have, let's see, let's find a good example here, a very basic example. Lithium. Okay? Lithium has 3 protons, but an atomic mass of 6. Okay? So it's got 3 protons and 3 neutrons. Oxygen. Where's oxygen? Right there. 8. Atomic mass, 16. We're going to round 9.9994 up, okay? So 8, 16, 8 protons, 8 neutrons. Cool? So what happens if I change the number of neutrons? I change the what? I want to hear it from someone over here. Changing the number of neutrons will change what number?
Mass.
The mass, exactly. The element stays the same element. The ion, if it's an ion, stays the same charge. Changing a neutron in or out will just change the mass. Now, a change in mass can sometimes be okay and sometimes not okay. If the element doesn't really care, if it doesn't really respond in any way, we call that a stable something, a stable isotope. Here's the word. Changing the number of neutrons makes it an isotope. If my element doesn't really react to the change in mass, it is a stable isotope. Example of this is carbon. Carbon comes in 3 flavors. Carbon-12, which is your basic plain vanilla. Where's carbon over here? Right there. Atomic number 6, atomic mass 12. How many neutrons does it have? 6, typically. Plain vanilla carbon has 6 and 6, okay? But carbon-13 is an isotope we see all the time. What's the difference? For carbon to have a mass of 13, what must have changed? The number of neutrons has changed. In what way? It gained a neutron. Yes! So when you add a neutron to carbon, you get carbon-13, which is a stable isotope. Add 2, you get carbon-14, which is more or less a stable isotope. It sticks around for a while. The ratio of carbon-13, 12, and 14 in certain substances gives us a lot of information about that material. My master's thesis was a carbon and oxygen isotope analysis of fossils in Oregon to recreate the paleoclimate during the last ice age. How did that work? Well, carbon-13 has a little more mass than carbon-12, which means that it's going to respond to environmental parameters a little different. You get more carbon-13 when you have an increase in temperature. Oxygen-16 versus oxygen-18. Oxygen-18 has more mass than oxygen-16. So when you're forming water in the atmosphere, the oxygens that have more mass tend to get incorporated into the water and fall as rain before the oxygen-16s do. So if I have more oxygen-18 in my fossil, that tells me that there was more rainfall. More oxygen-16 tells me there was less rainfall, or I was further from where the rainfall usually happened. So by knowing these trends and knowing how these isotopes respond in nature, we can make really cool observations about our world and especially the history of our world. Okay? So this is a really cool way that we can use isotopes. Now there are other ways we can use isotopes. For example, you have unstable isotopes. Best example of an unstable isotope is one you've probably heard about, uranium. You've heard of uranium before? Where's uranium on our periodic table of elements? What number is it? I see you pointing, but 92. Meaning it has how many protons? 92. Its mass is 238. Normal vanilla uranium is uranium-238. The uranium that we will typically use in a reactor is uranium-236. A nuclear reactor will typically use uranium-236. What's changed? Lost 2 neutrons. It has become an unstable isotope. Okay, now here's the problem. Unstable isotopes don't like being an isotope. So they are going to blast particles off of themselves, electrons, neutrons, and protons, until they reach a new stable condition. What did we learn about stability? In general, all things in nature are seeking stability. Unstable isotopes are blasting particles off of themselves until they reach a new stable condition. In the case of uranium, it's going to blast electrons, protons, and neutrons away from itself until it becomes lead. By the time it has done that, it's lost 10 protons, who knows how many electrons, and a bunch of neutrons. Okay, to go from 236 to 207. Okay? So, this is how a nuclear reactor works. You get a bunch of unstable uranium-236. You make basically a rod out of it. It's got to be about 40 to 50% uranium-236 for this to work. Okay? And you put 2 rods or more, if you want to make more energy, of these unstable isotopes next to each other. And the amount of radiation, those particles that they're blasting off of themselves, the amount of the radiation that bombards each other, super activates, and they zip into each other, they're constantly slamming into each other, making even more energy. The amount of heat released from these reactions is incredible. So then you surround this reactor with water. The water gets superheated, turned to steam. That steam is used to turn a turbine. Boom, you have a nuclear reactor. That's how they work. That's uranium-236. Now, we also like to use uranium isotopes and other types of unstable isotopes to determine how old things are, because the amount of time it takes for that uranium to break down into lead is consistent, constant, the same here on Earth and across the universe. It takes the same amount of time for that process to happen, which means this is the only true thing we can use as a clock for comparing anything against. So I told you before that the Earth is 4.543 billion years old. How do we know that? The oldest rock we found on the moon, right? I told you about that. But how do we know how old that rock is? We measured the ratio of uranium to lead. However much uranium there was versus however much lead there was tells us how old that thing is. It's the same for every other unstable isotope as well. They all have some stable daughter isotope, we call it, that they turn into. And the ratio of the unstable parent to the stable daughter tells us how long it's been that this process has been going on in that object. Isn't that awesome? This is called radiometric dating. That's where we get actual years from. That's why I can say 4.543 billion. Cool, so we can use unstable isotopes to date things. Fantastic. We can use them to make energy in a controlled environment like a nuclear reactor. Fantastic. Can you think of another way that we can use unstable isotopes? What about an uncontrolled reaction? This is where nukes come from. Nuclear weapons have the same concept as a nuclear reactor. You are initiating an unstable reaction, but instead of putting it in a controlled environment where you dictate how much energy, how much output this reaction is having, you specifically set off a cascade reaction that cannot be controlled. In a nuclear reactor, well, first of all, let me back up here. When you have unstable isotopes that are interacting with each other, they're going to put off a lot of neutrons. The more neutrons there are blasting out of these particles of unstable isotopes, the more energy is going to be released. Okay? We control this in a nuclear reactor by soaking up all those extra neutrons. We use graphite. There's a mineral called graphite you're going to learn about in this class. It's made out of pure carbon, 100% carbon. We use graphite. It has a property where it will just soak up all of those neutrons. It will absorb them, and that's how we control things in a nuclear reactor. In a nuclear bomb or a missile, any kind of weapon, you specifically don't have any controls like that. You set off this cascade, the neutrons cascade out of control, kaboom, sets the atmosphere on fire. That's what a nuclear bomb does. You're literally ripping apart elements, releasing the energy held inside of them all at once, and it sets the atmosphere on fire. Only 2 nuclear weapons that have ever been used in violence. Do you know where they were?
Hiroshima.
Hiroshima was one, and Nagasaki is the other. I've been to both places. I lived in Japan for 4 years. I've been to both detonation sites, walked inside the craters of both. I've been to the Holocaust, the nuclear Holocaust museums they have at those places. They have pictures of people taken right after the detonations. Fire dissipates away. People are stumbling out of the city. They're melting because radiation literally dissolves your cells or rips them apart. It's not a pretty picture. This is what it does. The largest nuclear explosion ever made. Have I already told you about this? Did I tell you about this? The largest nuclear weapon ever detonated on this island up here. Oh, the camera. Camera's not following me. Stay with me now. Problem is, if I take it over there, it's probably going to stay stuck on someone else's face. We'll see. You going to follow me? Hello. There we go. All right. This kind of banana-shaped island right here above Russia, that's where the largest nuclear weapon was ever tested. Why is it not doing it? All right. For those of you that are watching this online, pull up a picture of Russia and look at this large banana-shaped island above it called Novaya Zemlya. Okay? Right there. That's where the largest nuclear weapon was ever tested. It was so powerful. They call it the Tsar Bomba, by the way, the King Bomb. It was so powerful, it shattered windows across Europe and set off earthquake detectors across the entire planet. Like, they set it off up there to keep it a secret. Everyone knew about it. You don't blow up a bomb that big that has that kind of effect and people don't find out about it. It's the only bomb of its kind that's ever been tested because immediately afterward, the world came together and agreed no one is ever allowed to use one of these. You would need a couple of dozen conventional nuclear weapons to reduce us to the Stone Age. You would only need about 5 of these, specifically placed in places around the world. Okay. Of course, everyone agreed that we'll never ever use these things, but you know everybody has them. There's no way everyone doesn't have these things. Someone has it. If anybody thinks that somebody has it, everyone's gonna focus on having it. More like a deterrent. Man, my camera is. I think it is. It's stuck over there. Let's try and fix that. All right, I'm going to unplug it and plug it back in. No, I can't do that because I'm recording. Gosh darn it. Come on. Maybe if I come closer. You know, look at me. Hey. Right here. My online students are getting real personal with me right now. Right here. There? Yes, there we go. I've had this camera for 3 years. It might be time for a new one. Okay. Yeah, that was the Tsar Bomba. It was not, however, made through an uncontrollable nuclear fission reaction. Fission is the division of an element to make energy. That's what isotopes do. There's another aspect of this called fusion. You ever heard of fusion? If fission is the breaking of elements, what is fusion, do you suppose? Combining. Yes. The Tsar Bomba and other bombs of its like, which we call fusion bombs, do not operate through the destruction of elements, but by forcing the fusion of elements. Fusion, the act of fusion, creates incredible amounts of energy. Can you think of an example of fusion that goes on every day that we take for granted? The sun. The sun is constantly fusing elements together and making other, larger, more complex elements on the periodic table. That's what makes all of the energy in the sun, releases all that heat, all that radiation. It's fusion. We can do that on the very small scale and make the largest bombs ever made. Just one fusion reaction will do that. And that goes on trillions of times a second in the sun. Okay. The power inside of these atoms is incredible, right? Any questions about this? Fission, fusion, nuclear, isotopes, anything like that? Okay. Then let's go from talking about elements to the next step up, broadening our view a little bit to talk about minerals. All right. There are lots of definitions for the word mineral. There's a healthcare definition where people kind of treat the word mineral as synonymous with vitamins. There's the mining definition where they treat anything that you can remove from the ground for any economic value. They call that a mineral resource. But that includes things like oil, and even water is considered a mineral resource. Okay? The geological definition of a mineral, though, is any naturally occurring inorganic solid that possesses an orderly crystalline structure and a chemical formula. This is another thing that I'm going to need you to know word for word. Not memorize, write it down. Okay? You will need this in your notes. Any naturally occurring inorganic solid that possesses an orderly crystalline structure and a chemical formula. And can be represented by a chemical formula. So what's the difference between a mineral and a rock? Well, the best way that I can describe this to you is, let's see, Ulani, do you like chocolate chip cookies? Good, you have good taste. I do too. If I came up to you with some flour in my hand and said, here, have a chocolate chip cookie, Ulani, what would you say? It's not a chocolate chip cookie, is it? You'd look at me like I was nuts. Would you look at me different if it was salt? Okay, if I had just like a stick of butter in my hand and I came and gave it to you and I said, have a chocolate chip cookie, would you look at me like I was crazy? Yeah, this is exactly what I'm talking about with minerals and rocks. A mineral is not a rock. A rock is made of minerals. Minerals are ingredients that make rocks. In the same way that any of you would look at me crazy if I tried giving you a stick of butter and calling it a cookie, a geologist will look at you if you come up to them and give them a mineral and say, look at this rock. So now you know the difference. Rocks are made of minerals. Minerals are not rocks. Okay? So please use that terminology appropriately from this point forward in the course and in any assignments you turn in. Okay? Mistake to talk about chocolate chip cookies at 10:15 in the morning. I know, but here we are. All right. Minerals have properties. This is how we identify them from each other. Tell them apart. This is, and by the way, after you've identified minerals, you can figure out what the rocks are, right? That's part of figuring out a rock. But the properties that minerals have are unique to that particular mineral. It's kind of like DNA, where each of you has a slightly different DNA code or a fingerprint that is slightly different from each other's. Okay? Every type of mineral has some slightly different property value. You're going to be learning how to identify those properties now, and these are the things you're going to be identifying in the lab that we're going to start later on today. Okay? So we've got optical properties. This is the way that light interacts with your mineral. Okay? Does light pass through it? Does it reflect off of it? How does it reflect off of it? Crystal shape. Minerals will often grow into certain geometric shapes. We will learn how to identify those here in a little bit. The strength or hardness of your mineral relative to other common objects like steel or glass. Okay? Then you got things like density. It's a measure of mass and volume, right? We're not actually going to measure that in this class. If you need it, I will give it to you. Taste. Taste is a valid property of minerals. Feel free to taste any of these minerals, except for and please pay attention to this, samples 18 and 37. I'm giving you 51 samples to look at. You only have to identify the 24 on the lab, but I have 51 possibilities of what they might be. Do not taste 18 and 37. If you do, please tell me immediately and I will call poison control. Okay? One is a lead sulfide and the other is an arsenic sulfide. Don't do that. Okay? All right. Texture, how does it feel in your hand? That's another property. The smell, some have a unique smell, right? Like sulfur is common, like it's pretty common knowledge. It smells like rotten eggs, right? I should say rotten eggs smell like sulfur because that's what makes them smell like that, okay? Magnetism. Some minerals are going to be magnetic. Valid property to record. Effervescence. What does effervescence mean? Do you guys know what effervescence is? Effervescence is bubbling. I told you about this last time. If you put some acid on a sample and it starts to bubble, it's effervescing. There are only a few samples in this lab that are going to do that, okay? And a few samples in future labs that will do that. Really, the only mineral that does that easily is called calcite, and you're going to learn about that here in a bit. All right, so let's talk about these properties one by one. Your optical properties. Luster. Luster is the way that your mineral, that outer surface of your mineral, interacts with light. So descriptions of luster would be it's metallic or glassy. Vitreous is another word for glassy, by the way, you might see. Pearly. Resinous. It looks earthy. It's just kind of describing what the outer surface of your material looks like as light is interacting with it. Then you've got your actual optical property, which is how transparent it is. If it's transparent, light and an image will go through it like glass. If it's translucent, light will go through it, but no image. Think frosted glass. If it's opaque, no light will go through it whatsoever. Okay? Then there's the color. It's going to be very tempting for you to try and use color as your primary method of identifying what you're looking at. Ignore that temptation. Color is actually one of the last things that we care about. Why? Well, because color is based upon maybe only one or two elemental parts of your whole mineral, not the mineral itself, okay? Color is often just the result of one or two elements. And so I can have two copies of the exact same mineral that show up as different colors, like this. These are the same mineral, different colors. But you would be tempted to say that those are two different minerals if you're just looking at the color. Ignore the color. At best, well, record it, don't ignore it. At best, it'll be a tiebreaker because you can have two samples of the same mineral that are different colors or two different minerals that are the same color. And that can be very confusing if you only use that, ignoring every other property. Okay? Streak. You're going to record streak by scratching your mineral on the black and white ceramic plates I have in your kits. Okay? The streak is just, it's basically going to be a layer of the mineral that's only a few atoms thick. So it can give you a great perspective as to what the true color of your mineral might be as opposed to what it appears to be on the outer surface. Okay? So you'll record that and that's just going to be a color. If your mineral does not leave a streak behind, that means it's harder than your plate. Okay? Which is other valuable information. But for any of these properties, by the way, when you're working on these in the lab, if at any point something like that happens, no streak is left behind, you would just put Na or none. That's totally fine. If at any point you cannot figure out what the property is, I have no idea what this is, put Na. That's fine. To an extent. You can't put Na for every property or you won't have enough data to figure out what the thing is. Okay? You got to have enough. You got to collect enough to put the pieces together. But if every now and then you're just stumped, I don't expect you to make something up. That's not what we do in science. We acknowledge when we don't have enough data, but we still try and use the data we have. Okay? All right. Some shapes. Okay, so common geometric shapes. I mean, there's so many different shapes, and I'll give you a website, access to a website that shows you what the different shapes are. But a few examples. These are octahedrons, okay, made out of a mineral called apatite. Dodecahedrons. Garnet will often form in dodecahedrons. Garnet is a gemstone. Okay? It makes that shape naturally. Those were not cut. Okay? 12-sided shapes, dodecahedron. This is a cube of halite. Halite, by the way, is the mineral name for salt. Salt forms cubes entirely on its own. That's its crystal shape. Also, crystal form is a different word for crystal shape. Tenacity is the way that this material responds to stress. So, for example, a material that, like gold, would be called malleable. Why? Because it will bend, it'll shape. We can use pressure to make it into the shape we want. That's a malleable tenacity. Brittle means that after enough force is applied, it breaks, it shatters, okay? Like glass would. Elastic. You apply force to it, and then after the force is removed, boing, it goes back to its original shape, like a rubber band. Stuff like that. Hardness. Hardness is how your mineral is resistant to scratching. Now you test this with the piece of glass in your test kit. Glass on Mohs scale of hardness, which goes 1 through 10, where 1 is talc, the softest mineral, and 10 is diamond, the hardest mineral. When you glass is right here at 5.5 on the hardness scale. It's about halfway. So when you test your mineral on that piece of glass, you're going to see if it leaves a scratch behind. If it leaves a scratch behind, what does that tell you?
It's higher on the scale.
Higher than what?
5.5.
Higher than 5.5. So you'll just put greater than 5.5. If it doesn't leave a scratch,
It's low on the scale.
lower on the scale, and what are you going to put?
Less than 5.5.
Less than 5.5. There you go. That's it. Okay. All right. Mineral cleavage. This is probably the most difficult one for people to grasp. Hold on a second. Most difficult, and because it is, I made these. A couple of years back, when I was trying to teach mineral cleavage, and for the 100th time, people were just not getting it, I went online and tried to see if anyone had made any mineral cleavage models that I could just buy and keep in the classroom. And unfortunately, the answer was no. No one had taken the time to make that. So I did. I have a patent outstanding on these, waiting for final approval. But I made these. These are 3D printed plates that I put into different geometric shapes that represent cleavage, mineral cleavage models, and they attach together with magnets. So, cleavage is the manner in which a mineral breaks based upon its internal atomic structure. Whew, that was a lot of words, right? Let me explain this. Remember when we were talking about bonds, right? Bonds have a certain strength that when you surpass it, they break apart, right? Like if I were to rip a piece of paper or use a hammer to break a rock, I am separating atoms from each other, removing those bonds. Not all bonds are equally strong. So if I have a mineral that has several different types of bonds, maybe between hydrogens and carbons, and then hydrogens and oxygens and carbons, or whatever, they're not going to be equally strong to each other. So one type of bond is going to break before the other one does when I subject it to pressure. And when it does, because a mineral is just a repeating pattern of an atomic bond built on itself, it's going to break in the same direction through the structure of that mineral. And that is called a cleavage plane. It's a flat surface along which my mineral is going to break. So, when my mineral has one plane of cleavage, that means one plane of weakness, and then its atomic structure, you're going to get something like this. It's going to look like stacked plates on top of each other because it's breaking only in one direction. Like that. Okay? When I have two planes of cleavage, ruh-roh, a magnet needs to be re-glued in that one, I guess. When I have two planes of cleavage, Then it gets a little more complex. Because so many minerals have two planes of cleavage, we have to now start looking at it with another characteristic. The angles at which those cleavage planes intersect. Now, don't worry. I don't need you to pull out a protractor. You don't need to tell me the actual angle. All I need from you is it greater than or less than greater or less than 90 degrees, so not at 90 degrees, or does it appear to be at 90 degrees? That's the only angle you need to give me, those two options. Not at 90 or at 90. When I have two planes of cleavage at 90 degrees, I'm going to get something like this, where I've got one plane here and another plane here. And the angle at which they meet, 90 degrees. Okay? Man. Oh, where'd the magnets go? They popped out right there. I'm going to have to re-glue that. All right, I'm going to pass these around. Please be careful so we don't lose these magnets. Let's start these right here. One plane, two planes at 90 degrees. Two planes not at 90 degrees. It's going to give me... Why are you all messed up? I don't know why that's not working. I think that the magnet polarity is not right for this one. I'll have to figure that out later. It's going to look like this, where I have two planes here and here, but they meet at not 90 degrees. See, that's an acute angle and that's an obtuse angle. No matter how I look at this, the two planes of cleavage are not at 90 degrees. Okay? I think one of these might be missing too. Oh well. All right, so that's it for two planes. Now let's talk about three planes. When I have three planes of cleavage, it's going to make a box because there's going to be 1, 2, 3 at 90 degrees. Boom, boom, boom. Makes a box. And if this were to break down into smaller pieces, you know what? It would break down into smaller boxes. Three planes of cleavage at 90 degrees. Now, notice I am not saying sides. I am saying planes. For a shape, you would count the sides. And I want you to for crystal form. For cleavage planes, only count the planes of breakage. When I say plane, I'm talking about a direction. So for example, this plane is the same as this one because they are parallel. So even though there are two sides, if I were describing the shape, I would look at those as sides. Because I'm talking about these as planes of direction, they are the same. So even though I just passed around a six-sided object, I called it a three planes of cleavage, right? Same thing here. This is three planes not at 90 degrees. It kind of makes a rhombus where here you have 1, 2, 3 that are breaking, and none of these angles are at 90 degrees. And it will break into smaller rhombuses like that. And then the last one that you'll see in my class, because I'm not mean and I didn't give you all of them, I only gave you the most basic kinds, right, is four planes of cleavage. So 1, 2, 3, 4. And you know what? Each of these is a separate plane, but they are mirrored on the bottom of the shape. This plane and that plane are the same because they are parallel. Okay? Four planes of cleavage. Any questions about cleavage? Oh, the camera's stuck over there. Hello, I'm over here now. Come with me. Come with me. There we go. All right. When my mineral does not have cleavage. That means that all of its bonds are approximately equally strong to each other. Okay? So it's not going to have cleavage, it's going to have fracture. It's going to break in it's going to be kind of random. But there are some distinct types of fracture that you'll see. The most distinct one is this one. Quartz, for example, has no cleavage. Its bonds are all equally strong in every direction. So it kind of gets this scooped out, ripply look when you break it, kind of like certain types of glass do. Really thick glass will break like this as well. We call that conchoidal fracture. Okay, so you get fracture when you don't have cleavage. All rocks are going to break. This is describing the way that it breaks, either with cleavage or with fracture. We've already talked about density. You're not going to worry about density in my labs. Some places do. I choose to focus on other things that are easier to measure with your hands and your eyes and a few basic tools. Density is something that you need some specialized equipment for. So we're not going to focus on that. Other properties we've already talked about. There's taste, texture, all of this stuff. Please make sure you don't taste 18 and 37. You can handle them with your hands. Just wash your hands afterward. Yeah. Any questions about properties? All right. There are over 4,000 different types of minerals, and that number grows every year pretty much. We got 8 weeks. Who's ready? I'm kidding. I'm not going to make you do that. No. You were about to kill me. No. So we're only doing 51 on the practice set, but you only have to identify 24 for the lab. Okay? Which that already is way less than I had to do. I had to learn 200 samples when I took physical geology, but that was 13 years ago almost. Yeah, 13 years, wow. But that's not necessary at this level, okay? You don't need to know all of that. You just need to know the basic ones that you're most likely to interact with throughout the rest of this class and throughout your life. So that's what we're going over. So we're going to start off by breaking minerals down into two categories: silicates and non-silicates. Silicates make up just over 90% of the Earth's crust. And non-silicates fill in the rest of that. Okay? Silicates are built around the same central structure. We call this a silicon tetrahedron. This is a covalent bond between one silicon that has a +4 positive charge and 4 oxygens, each of which has a -2 charge, which doesn't sound like it should work, but this is how covalent bonds work. They share the positive charge for the silicon, okay? Constantly zipping around it, constantly shifting between each other, constantly sharing this, which gives this whole thing a net charge of -4. Because you have +4 here and -8 between all these oxygens. Negative charge 4 in the net, okay? Which means that this is still looking to bond with other stuff. And what does it bond with? Metals. When this bonds with metals, we make our, and other atoms, not just metals, but when it bonds with other elements, it's going to bond with metals first, but we'll talk about that in a second. We make our silicate minerals, okay? Repeated structures of this, okay? Silicon tetrahedron, that is the foundation. That's the first thing that forms that silicates can form around, okay? So when this happens, we can have independent silicon tetrahedrons like this. Then, and I'll just say this now, this is something that's going to come up when we discuss igneous rocks later on. Think of this happening, this progression I'm about to talk about, as something that happens as magma cools off. When magma cools off, all those super high energized atoms start to make bonds with each other. The more cooler it gets, the more bonds that form. The more bonds that form, the more complex mineral structures you get. So as we're losing temperature, we're going from independent tetrahedrons to single chains, then double chains, then sheet structures like this, making almost like piece of paper kind of looking minerals. And then three-dimensional frameworks, the most complex, interwoven, stuck together kind of tetrahedron shape. Okay? Okay. When the silicon tetrahedrons have formed with that net negative charge, what's the next thing they're going to want to do? Bond with something else and satisfy that -4 charge. So what are they going to bond with? Well, here we have, conveniently, magnesium and iron, two very common elements on our planet, each of which has a +2 charge. So that's very common. We're going to bond with things like iron, magnesium, potassium, sodium, aluminum, calcium, all these things. And this is what's going to make the bulk of our silicate minerals. Combinations of this silicon tetrahedron and those minerals. These, these elements. Do these look familiar, by the way? These 6 elements here? What do they remind you of? Have we seen that list somewhere already? Maybe from Tuesday? Maybe it's in someone's notes somewhere? Hopefully.
What was your question?
Have we seen this list of elements somewhere already in the class?
Oh, the 6 of the Earth.
What part of the Earth specifically? You're on the right track, but no.
The crust.
The crust. Okay? Yeah. These 6 elements, in combination with 2 others, make the majority of the Earth's crust. What were the other 2 elements?
I'm not there yet.
This is from Tuesday. There were 8 elements that made up the majority of the Earth's crust. These 6 and 2 others.
Iron, nickel, magnesium, iron. Oh, silicon, aluminum.
Silicon is 1. What's the other one not on this list?
It's either sodium.
Sodium's here. Not on. It's not one of those 8. Huh? Magnesium's on this list.
I don't know. Calcium.
Calcium's on this list. Silicon is one that's missing. What's the other one? Oxygen, yes! Silicon and oxygen are the 2 of 8 that make up most of the crust that are not on this list. Why aren't they on this list? Because they're in the silicon tetrahedron. Boom! Full circle. Here we are, people. Okay, so those 8 most common elements are also the 8 most common ones that make silicate minerals. Okay, so silicon tetrahedrons are made out of the silicon and oxygen, and the other 6 make the things that bond with them the most. Ergo, why most of the crust is made out of it. Look at that. It comes around. Okay, magnesium, iron. They tend to bond very quickly. Now, every now and then, aluminum and silicons will swap out with each other. It's not terribly common, just something that's interesting. Magnesiums and irons will swap out with each other very easily because they are about the same size and they have the same charge. So there are going to be variations of certain elements, like a mineral called olivine, which you will see here in a minute. There's variations of olivine made out of iron and variations made out of magnesium. They are both olivines because they have the exact same structure. It's just that because irons and magnesiums have the same charge and the same shape and mass, pretty much, they can swap out with each other very easily in that bond. Okay. So let's talk about the more common silicate minerals. We've got dark silicates and light silicates. We call dark silicates because guess what? They are dark colored. And light silicates because they are light colored. Easy way to tell them apart. Okay? Dark silicates tend to form first as our magma is cooling down. Light silicates tend to form last. Okay? So just to kind of make you remember this, here's our temperature. This is probably a terrible color to use for the camera. And it's probably not picking up orange very well on this background. So let's switch to, I'll just use the black one, I guess. Okay, so temperature. Oh my gosh, this pen is already bad. Temperature is decreasing as we go down through the sequence we're about to do, okay? So here we have high temperature. We're going to have independent tetrahedrons, and they are going to bond with metals, iron and magnesium, and that's going to give us olivine. Okay? Decreasing in temperature. Now we're forming our single chain silicates. That's going to give you something called pyroxene. Still clearly dark silicate. Then moving on down, we get our double chain. That's going to give us amphibole. Still clearly dark silicate. Moving on down, biotite, dark silicate sheet structure. Then we get a light silicate sheet structure called muscovite. I'm going to talk about each one of these individually here in a minute, by the way. Okay? Then we get our 3D frameworks, including feldspar, which is a light silicate, and quartz, which is most definitely a light silicate. Okay? So as we're losing temperature, we're going from dark silicate sequence down through a light silicate sequence, from independent tetrahedrons to the complex three-dimensional frameworks. Heat is a very important factor here. Heat determines how easily and what kind of bonds can form. Okay? I'm going to throw this black pen away. It's not writing very well, and its ink is very difficult to erase off. All right. So let's start with our light silicates. Let's go down through our sequence of light silicates. Feldspar. Feldspar is probably the most common silicate on the surface of our planet. We estimate that the crust is maybe 50% feldspar of one kind or another. There are many different varieties, but they share most of the same characteristics. Okay? Feldspar, its properties, has two planes of cleavage at about 90 degrees. So this is an unbroken feldspar crystal right here. You can see it's got this really cool shape. It looks like two crystals that grew into each other. We call it twinning. I love this sample because it's twinned crystals of feldspar. So when you were looking for crystal shape, you would count the number of sides here. You would go to that website, which I'm going to tell you about here in a bit, and you would find the shape there. But its cleavage, when you break feldspar, it has two planes of cleavage at 90 degrees. So you're going to look at this, and you're going to see, oh my goodness, okay, yeah, look at all these broken surfaces here, but they are also flat and reflective. Obviously broken, also obviously flat, right? Clearly a cleavage plane. So you're going to count how many cleavage planes there are. Well, there's not one here, and there's not one here on this end, but that's definitely one, that's definitely one, that's definitely one, that's definitely one. There are four flat, broken sides here, but two of them are parallel to the other two, meaning we have two planes of cleavage. And about what angle does that look like it's at?
We've discussed I'm blind.
Fair enough. Jared, about what angle does that appear to be?
Like,
Not at 90 or 90?
95 degrees?
Okay, but you'd say it looks like it's about 90.
yeah, like it's-
Yeah, okay, so that appears to be two planes of cleavage at 90 degrees. And there we are. Okay? All right. Its luster can vary, go somewhere between glassy, which is, you know, it looks like one version of glass, maybe semi-transparent, something like that. Pearly, anything like that. And there are two different types of feldspar. I'm going to start these going around this direction. Okay. There are two different types of feldspar you're going to learn about in my class. You've got potassium feldspar and plagioclase feldspar. Potassium feldspar is what I'm passing around right now, what I just showed to the camera. It comes in a variety of colors. You'll usually see it in some kind of lovely kind of sea green color. We call that Amazonite feldspar. Or this kind of salmon pink color, okay, which is just potassium feldspar is what we will typically call that. Plagioclase feldspar has most of the same properties, but one distinct difference. When you look at plagioclase feldspar at the cleavage planes and you kind of reflect it in the light, you will see parallel grooves running along the cleavage planes. We call those striations. This is the easiest way to tell potassium and plagioclase feldspar apart from each other. Look on the cleavage planes for those grooves. And for my online students that are doing this using my YouTube videos, I do pause for a minute in those videos so that you can kind of see reflected in the light those cleavage planes. So you'll just need to pause the video at the right moments to look for that. Okay. Then we have quartz. Everyone's familiar with quartz. Everyone knows quartz. Quartz is awesome. Quartz comes in a lot of different flavors. Okay. Quartz is made entirely out of silicon and oxygen, by the way. It is a silicon dioxide. One silicon, two oxygens. Three-dimensional framework of that silicate tetrahedron structure. It's one of the last things that forms when my magma is cooling off. Right at the end of the magma chamber's life cycle. We'll talk more about that next week. It doesn't have any cleavage. It has conchoidal fracture. It's a hardness of 7 on the hardness scale, which means it'll scratch most things. It will scratch glass. It will scratch your streak plate. It won't leave a streak behind. What gives it all its colors, though? Because quartz is so many different types. We got milky quartz, smoky quartz, citrine, amethyst is a type of quartz, rose quartz, tiger eye is a type of quartz. I mean, there's so many different varieties. What gives us all of these different colors, these different varieties of quartz? Any guesses? It's not temperature. It has to do with whatever is stuck inside them. Whatever extra elements were left behind and got incorporated into the crystal as it formed. For example, amethyst is purple because there's some extra iron in there. Smoky quartz is brown or gray because it has some uranium in it. Rose quartz has a little bit of potassium, right? Milky quartz has a little calcium, so on and so forth. Whatever extra stuff got incorporated into that quartz as it was growing, that's what makes its colors. All right. Muscovite. Muscovite is the light silicate sheet structure. Okay. It makes very flat, page-like sheets on top of each other, and you can kind of see that here. These are a whole bunch of different, I guess you could call them kind of almost books of muscovite that have grown into each other, but each one of these will split apart into different sheets. Okay. Ladies, if any of you use makeup that has glitter in it, that's usually crushed muscovite. Okay. Clay. Clay is often the result of weathered, aka broken down, light minerals, light silicate minerals. So it's gone through some breaking down. It's turned into kind of this fine dust stuff. We will use that for different things. This is what we call a secondary mineral. Clay will come back into the conversation when we learn about sediment and sedimentary rocks later on. But it's a secondary mineral. And we use it for a whole bunch of stuff. It's the basis for things like cement, concrete. Who likes milkshakes? I love milkshakes. Have you ever wondered how they get that consistency of making it kind of like liquid enough to drink, but thick? It's not like a true liquid, but it's also cold enough that it should be frozen. You add clay. You put clay in there. That's how it gets that weird consistency. Yeah. I'm not going to say you're drinking dirt, but, you know, if the boot fits. All right? All right. Those are light silicates. For dark silicates, so going from these high temperatures down towards this mid-range here, and I'll explain why that happens next week, why we get the differentiation of dark and light silicates here next week. Just remember, for now, this happens, and it will make sense next week when I finish explaining the process. Starting off with olivine. Olivine is this lovely green mineral, and I'm going to pass this around. Olivine and peridotite, which is the black mineral you see in there with it, make up, as far as we can tell, olivine and pyroxene. I think it's a peridotite. This whole thing is called peridotite. Olivine and pyroxene make up, as far as we know, most of the mantle, which is underneath the crust, right? I absolutely love olivine. The color of olivine is like my favorite. Olivine is hard, about a hardness of 7. makes very small, kind of roundish crystals. It doesn't have a fracture, or it doesn't have a cleavage. Very, very high temperature mineral, which means it breaks down very quickly under surface conditions because, in general, all things in nature are seeking a state of In general, all things in nature are seeking a state of stability. It's not stable up here, so it breaks down until it reaches something that is stable. Okay? That's olivine. That black mineral in there with it, that's called pyroxene. It's the next thing that forms as our magma continues to cool off, making this kind of blackish mineral. Okay? Two directions of cleavage at 90 degrees, just like feldspar. Just obviously this is a dark silicate, where feldspar was a light silicate. Okay? Now this next one is often confused with pyroxene. It's called amphibole. Okay? Amphibole and pyroxene are often confused with each other. The best way to tell them apart is the cleavage. Amphibole has cleavage not at 90 degrees, actually very far from 90 degrees, 60 and 120. But it's going to be very different enough from 90 degrees you should be able to tell the difference in the lab. Okay? Color-wise, they're very similar, which is why I'm telling you to ignore color unless it's a tiebreaker. Okay? So look at the cleavage very carefully and make sure that you don't confuse these two for each other. Then we have biotite. Biotite is the sheet structure, dark silicate mineral. Like muscovite, the kind that got crushed up and used for makeup, except this one is black, so we don't really use it for that. Okay? Doesn't really make that silvery glitter that people are looking for. Garnet is, I like thinking of garnet as kind of like an extra. It's kind of a trash can rock. Excuse me, a trash can mineral. Because what I mean by that is it gets all the extra stuff that's left behind and kind of gets incorporated into garnet. Garnets are made out of a whole bunch of other types. There's a whole bunch of different types of garnet that are made as a result of whatever's left over in your whatever system made that garnet. You can get garnets made in a couple of different ways. Okay. Now let's talk about the non-silicates. So that was a brief overview of dark and light silicates, the most common ones. Now let's talk about non-silicates. Non-silicate minerals are grouped together based upon whatever ions they have in common with each other. Okay? So for example, calcite and dolomite both have a CO3 2 negative in common with each other, and so we put them into the same group of carbonates. These are the two that react to hydrochloric acid, by the way. Okay, calcite very vigorously. Dolomite, it has to get kind of powdered first before it will react. But calcite will react like this. Okay, halides, halite, fluorite, sylvite, different types of salt. Okay, oxides, hematite, magnetite, corundum, ice. Whoa, 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 whoa. Why is ice on here? Aren't we talking about minerals? That can't be right. Why is this on here? Someone give me the definition of a mineral again. I'm going to have to call this person that made this diagram. Get them to change it. What's the definition of a mineral?
Ingredients to rock.
No. No. I gave you the definition of a mineral and told you to write it down. I'll give you the first bit. Any naturally occurring. Right. So let's disprove ice right now. Any naturally occurring. Well, okay, I guess ice is naturally occurring. Inorganic. All right, sure. Solid. All right, fine. What's the next bit? Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by chemical formula. What's the chemical formula for ice? Guys, ice is a mineral. Oh my goodness. That's why it's on the list. That is why we have a whole lecture devoted to glaciers too, by the way, because technically speaking, glaciers, guess what, are made out of rocks. Because ice is a mineral, baby. Glaciers, the study of glaciology, is a subset of geology for this reason. Okay? So, ice, here on the list of minerals. Cool. Sulfides, sulfates, and then we have our native elements. Gold on its own, silver on its own, platinum on its own, carbon on its own. Comes in two types, right? Diamond, graphite. Okay? So these are the non-silicates, most of the non-silicate groups that we see in our world. Okay? And these make up about 8% of the volume of the crust, the rest being silicates. And we generally find these in sedimentary rock for reasons we will learn when we discuss sedimentary rock in a few weeks. All right, let's take a minute here to talk about mineral resources. Obviously, one of the primary reasons why we care so much about learning about rocks and minerals is because we need a lot of the resources that we find in them. Okay? Those native elements, gold, silver, platinum, carbon, we need those all the time. We need the other things too. We need random crushed rock for concrete, right? We need quartz to melt and make glass, right? We need salt for our food and for maintaining our roads, right? Anything that we pull out of the ground for a use in civilization, we generally refer to that as a resource. Okay? A reserve is some portion of that resource which we know is there and which we can utilize at some point in the future. Ore is a word that we typically use to refer to material that contains metallic resources. So we'll use things like gold ore, copper ore. I spent some time working at a gold mine in Nevada on their exploration team. So I helped them find, while I was there, we found a lot of gold. I think it was somewhere in the maybe like 20 million ounces potentially is what we estimated were going to be there for in this future pit we were going to dig for this gold mine. And boy, let me tell you, the resources that go into pulling gold and silver out of the ground, it's tremendous. We used haul trucks, 3 stories tall. You had to take flights of stairs up to the cab of this haul truck. The tires on this haul truck were 1 story tall. Imagine a 12-foot tall tire. They were capable of carrying 500 tons of rock at a time. They were so big that you could not drive in front of them. They would not see you before they ran you over. Right? It was an adventure working on this mine. I actually loved it. It was really cool, really fun. But the price of gold made a big difference for what kind of rock we could look for, what the quality of the ore that we could use was. We were targeting ore that had 0.03 parts per million of gold or more. At 0.03 parts per million. At 0.03 parts per million, we could still make a profit. It's even better now because the price of gold keeps skyrocketing. Okay? The price of your product plays a big role as to what kind of thing you can target. For example, this is the Bingham Canyon copper mine. For reference as to how big this pit is, those are mountains behind it. You can fit some of those mountains in this pit. They've been digging this pit for a very long time. Okay? The Bingham Canyon copper mine operated for a long time. And it was one of the principal sources of copper in North America. Okay? Copper being vital for our electronics infrastructure. Okay? I forget exactly when it was. I want to say maybe the late 90s, early 2000s. I forget exactly when it was. But some time ago, decades ago, China opened up a whole bunch of copper mines and flushed the market with copper, which dropped the price of copper. Price of copper drops, all of a sudden it becomes that much more expensive to run a copper mine. Because if the juice ain't worth the squeeze, you can't keep squeezing. It's not paying for itself. So the owners of this mine had a choice. They could either shut the mine down and let China have the market, or invest a whole ton of money in revamping the whole project here to make it cheaper to produce the copper. Lucky for us, they chose the last option. I want to say they invested like $100 million or something like that into redoing their whole thing and making it less expensive to get copper out of the ground. So they were able to compete with Chinese copper, and this copper mine is still operating for the most part, okay? And thanks to that, we haven't been indebted to China, at least for a lot of copper. We're indebted to them for a lot of other stuff that kind of have the world by the family jewels in a lot of different ways, if you get my drift there. But the price of your product has a lot to do with whether or not you can actually afford to pull a resource out of the ground. No company anywhere ever has ever and never will develop a product without the ability to make profit off of it. You don't have profit, you can't pay your employees. There's no reason to develop a product. No one just does it out of charity. Has to make a profit. Okay? All right. Any questions about that? All right, well, let me give you a little introduction to your Lab 1 then. Okay, lab, let's go here. Let's not freeze up on me, computer. Yep, okay. It still sees me. Okay, here we go. Lab 1, PowerPoint. Okay, mineral identification. I'm just going to breeze through this because a lot of this is stuff that we already talked about. I'm just going to give you some of the highlights, all right? So as you are going through identifying your minerals, here are some of the resources you're going to need. Oh, have you guys ever seen Journey to the Center of the Earth with Brendan Fraser? You're laughing. No? Okay, so Brendan Fraser plays a geologist in this movie, okay? And for context, he and this cave guide and his son are going down through a volcanic tube that no one has been in before. And they see some minerals in the wall. Let me turn this up so you can hear it. Okay, they see some minerals in the wall. Pay attention to which minerals each different person is focused on, okay? He's the geologist. That's funny for a geologist. So his son was like, or the cave guide was like, rubies. And his son was like, emeralds. And the geologist looked at the wall and went, feldspar. It's like the most common mineral on the face of our planet. And that's the one that he's focusing on. I love it. That's funny. It's funny if you're a geologist. All right. All right, so all the different properties that we've learned about, different types of crystal form, also known as crystal habit, also known as crystal shape. There's a couple of different examples there, a couple of examples here, but this is going to be your best friend. This link right there is going to be your best friend when it comes to identifying crystal shapes. You're going to go to this PowerPoint. You're going to download the PowerPoint. You're going to open that link. It's going to take you to a website. If you try doing it on OC Wi-Fi, it may or may not work. If you try doing it on an ECISD laptop, it may or may not work. Firewalls are a thing, and this website is hosted in .nl, the Netherlands. Okay, so if the firewall doesn't let you through, you might need to hotspot your phone and connect to it that way. Okay, but it has a list of all the possible crystal shapes separated by the number of sides it has. So if you're looking at your shape, at your crystal shape, and it has 6 sides, then you'll go to the 6-sided list and you'll flip through it until you find the right shape. And it's got really nice 3-dimensional rotating images, right? So you should be able to find the right one. Now here's a caution. So crystal shape is the shape that your mineral grew into, the geometric shape it grew into. What if my mineral is broken? Am I going to be able to tell crystal shape? Probably not. And that's a perfect example of where you would put NA. Not to say it doesn't have a crystal shape, just to say I don't have enough data to find it. By the same token, though, if your mineral is so broken that you can't get crystal shape, you definitely should get cleavage data. And the opposite is also true. If it's not broken enough for you to get cleavage data, you definitely should be able to have crystal shape. You should always be able to have one of the two most of the time. Okay? All right. So then there was cleavage. We already talked about that. The way that it breaks based on its internal atomic structure. These are just different ways of showing you the angles at which the planes of cleavage intersect at. Hardness, the ability to resist abrasion, if it scratches glass, if it doesn't. Color, we talked about that. Streak, we talked about that. Luster, I have on this slide a couple of different types of luster. This is vitreous, also known as glassy luster for obvious reasons. Pearly, kind of looks like mother of pearl, right? Like on the inside of a seashell. Resinous, looks like dried tree sap. Silky, like imagine like a silk scarf or something, the silk material, it's got that very glossy sheen on it. Greasy, looks like someone just sprayed it with cooking spray, right? Like Pam or something. Earthy, looks like dirt, right? Those are some examples of luster. Tenacity, just going over the different types of tenacity like I already talked about. Optical property, transparent, translucent, opaque. We talked about all of that already. Effervescence, it'll bubble in the presence of acid. Also, calcite, while it does bubble, also has this other really cool ability called birefringence. When you take calcite and you put it over something like words, it'll double the image. It's called birefringence, another cool property that can help you identify it. Magnetism, taste, so on and so forth. Okay, so this is your process. You're going to essentially go through elimination, process of elimination here. So you start off with a property, probably crystal form, because that's the first one I ask you about. You'll go through crystal form, identify the crystal form for all of your samples. Then you'll go through and you'll identify cleavage, and you'll go through and identify luster, and all of the things. And then you're going to process of elimination, figure out what each sample is based on the properties you collected for it. I strongly encourage you to work in groups, but you don't have to. Okay? You don't have to. It would just, might be helpful. Because you might think something. Then if 3 other people think something different, they might be able to help you understand why you were thinking about it wrong, Any questions about the lab? For my online students, obviously working in groups has limited relevance to you, but I do have the ability to put together a custom discussion board on Blackboard. So if you and anyone else in the class wants to make a kind of study group together or a lab discussion group or something, I can make a custom group that includes you and those people in it. Discuss it over GoReact. Let me know in email format who wants to be in your group, and I will put it together for you as soon as I can, okay? Any questions? Great. Well, you have 24 samples to identify and 2 weeks to do it. So I'm going to go ahead and end the recording here, and we can get started. I'll hand out those lab sets.